Let's go over properties of matrices. So far we've seen matrices in terms of augmented matrix solving a system of equations. We can actually treat arrays of numbers as objects themselves. So as math objects. In the same way that numbers can be treated as mathematical objects, or vectors can be treated as mathematical objects. So here's the idea. A matrix is full of entries. A11, A12, A13, dot, 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 A1n, first row, first column, first row, second column, first row, third column, etc. A21, A22, A23, dot, 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 A2n, second row, first column, second row, second column, second row, third column, dot, 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 to the mth row, first column, mth row, second column, dot, 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 mth row, nth column. So this would be an m by n matrix, where m is the number of rows and n is the number of columns. Matrices don't have to be square. In fact, they can be rows. You can have 1, 2, 3. This is a matrix. It's a 1 by 3 matrix. You could have a 1, 2, 3. You could have this kind of matrix. This is a 3 by 1 matrix. If a matrix does have the same number of rows as columns, it's called a square. So 1, 2, 3, 0, 2, 4, negative 1, 8, 0. This is a 3 by 3. This is an example of a square matrix. Square matrix. You can have other rectangular matrices like 2, 3, 0, negative 1, 8, 4, 1, 3. This would be 2 rows times 4 columns, a 2 by 4 matrix. So these matrices can come in all shapes, and we can do things with them. So there are some properties. We can scale matrices. So if A is a matrix, then negative 3 times A is also a matrix. And this is very easy to do. Suppose this was my matrix A. Then 3A, negative 3A would be negative 3 times this matrix, and this would be negative 6, 0, negative 24, negative 3, negative 9, 3, negative 12, negative 9. You just multiply everything in it by that number. So that's pretty easy to do. There's another operation called a transpose, and it's denoted, if you have a matrix A, it's denoted by a capital T superscript. So a capital T superscript. This operation exchanges rows and columns. So if we continue to use the example here, what it means is if we were to write down the transpose of A, then this column becomes a row. This row, this first row becomes the first column. So that would be 2, 0, 8, 1. The second row becomes the second column. 3, negative 1, 4, 3. And this is the same thing as saying the first column becomes the first row, the second column becomes the second row, and so forth. So you'll sometimes see this denoted as little a I sub j goes to little a j sub I. And little a represents, as it does above, right here, the entries of A, and this switching of indices represents swapping the rows and columns. So scaling and transposing, these are operations you can do to any matrix. There are some operations you can only do to certain matrices, like adding. Adding matrices is wicked easy. It's just like adding vectors. You add component-wise. So if I take two matrices, say 2, 3, 0, -1, 4, and 5, this is a 2 by 3 matrix. I can add another 2 by 3 matrix, 0, -1, -1, 4, 5, 0. This is another 2 by 3. And the way we add these matrices is component-wise. So I take the 1, 1 position of both matrices, and I add those to get the 1, 1 of their sum. So 2 plus 0 is 2. Now I take the 1, 2 of both matrices to get the 1, 2 entry over here. 3 minus 1 is 2. And I keep doing that. 0 minus 1 is -1. -1 plus 4 is 3. 4 plus 5 is 9. 5 plus 0 is 5. That's very easy to do. And the only thing you really have to remember is that matrices must have the same dimension to be added. That should make sense. If we're adding these component-wise, like we do vectors, it wouldn't make any sense to try and add a 2 by 3 and a 2 by 2. What would you add to the 0 and the 5? It doesn't make any sense. Okay. So this can't be done. Okay. Subtraction works the same way. You just subtract instead of adding. So that's adding matrices. They have to be the same dimension. Some matrices, actually, let's talk about, so multiplication is going to require a separate video. But you should see, at this point, the things that we've talked about doing to matrices are in fact the same things you do to vectors, and they're done the same way. In fact, we'll find out later that matrices are vectors. This is in fact pretty confusing, just from a language perspective, because matrices will also act like functions on vectors, even though they are themselves an example of a vector. So we'll cross that bridge when we come to it. So at this point, right, just looking back at the previous page, we've got how do we refer to the elements of a matrix? How do we refer to the dimensions of a matrix? Square matrices. How do we scale matrices? How do we transpose them? How do we add them? Those are things that with a little bit of practice you can do very easily, and I'll just expect you to be able to cover that on your own.